Good morning, everyone. We are very happy to have with us this morning both the rector of our university, Professor Gülay Barbarosoğlu, and Professor Alex Flippenko from Berkeley. The introduction this morning will be done by our rector herself.
Good morning, everybody. Today I'm not the rector, but I'm a student in this course, so I'm very, very excited. Dear students, today I'm extremely happy to be attending a humanities lecture, which is a very important course at this university, and it is our core competence, which helps to place you apart from students of all the other universities in our country. Personally and institutionally, we really emphasize the importance of humanities at this university. So you are very lucky to be here. Today, I'm further excited and pleased to welcome Professor Alex Flippenko, who has come all the way from Berkeley to give this week's lecture. So thank you very much for being with us. We are very lucky to have you with us. So I want to say just a few words and we'll leave the floor to Professor Cevza. And Alex Flippenko is an elected member of the United States Academy of Sciences, and he is one of the most highly cited astronomers in the world. So we are very proud to have you here. And I will leave the further introduction to you because you are the expert in this area. So thank you for being here. Thank you for giving us this lecture. I'm very proud to be a student in this course. Thank you.
I think I will forego further introductions. Our rector has told you who he is, what he's about. Please, Alex.
Thank you very much for that very kind introduction. It is my great pleasure to be here at Bogazici University. Did I pronounce that?
Yes.
Almost correctly, yes. It's a very nice place to be. I just arrived yesterday with my wife, Noelle, who I think is back there somewhere, way in the back there. And we look forward to a wonderful week here in Istanbul. I wanted to note that this is now 150 years for Bogazici University. That's fantastic. Congratulations. My own university, University of California at Berkeley, is 5 years younger than yours. So we're celebrating our 145th year. Maybe we should have Alpar come out at 150 and give some lectures, okay? So this is where I teach, and in fact, in this building right here, I have a lecture hall with 800 students. I teach an introductory astronomy class that's very, very popular among the students. And just on Friday, I finished my last class, and then the next morning we flew out to here. Well, let me start first of all, this is, of course, the first of two lectures, Cosmic Evolution. Today, I'll discuss our place in a universe of galaxies. And on Wednesday, I will discuss the formation of stars, planets, life, and the evolution of life, okay? So let's start by just asking, where are we? Well, of course, we're at Bogazici University, a very nice place by the Bosporus. Here you see the scene from the room where I'm staying. It's very nice. Of course, this is in Istanbul, which is in Turkey. So here's Istanbul, the crossroads between Europe and Asia. Wonderful place. Length of Turkey, maybe 1,500 kilometers. Width of Istanbul, perhaps 50 or 60 kilometers, something like that. Where is Turkey? Well, Turkey, of course, is on Earth. You can see it right here, right between Europe and Asia. Earth is about 13,000 kilometers across, all right? Our nearest neighbor is the moon. Here's the view of Earth from the moon. The moon is about 380,000 kilometers away. So I'm going from small scales out to bigger scales, all right? What about the sun? The sun is about 150 million kilometers away. That's starting to become a very large number. So we can think about it in terms of the length of time it takes light to travel from the sun to us. It takes a little over 8 minutes for light from the sun to reach us here. So we say that the sun is 8 light minutes away. You're not seeing the sun as it is right now. You're seeing it as it was 8 minutes ago, 8 1/3 minutes ago. Now, the sun is a typical star. When we look at the stars in the sky, they're just like the sun, but they appear faint because they're so far away. A typical star that you see in the night sky might be a few hundred light years away. So we're seeing it as it was a few hundred years ago. You're looking back in time when you look at the stars, when you look up at the night sky. And the stars are just distant suns. And you might wonder, do they have planets going around them? They do. I will discuss that on Wednesday. Now, a light year is the distance light travels in 1 year. It's about 10 million kilometers. So it's a very great distance. And typical stars are a few hundred, maybe 100 to 1,000 light years away. Let me show you a nice demonstration of the sizes of objects. Here are the planets. Earth is a small planet compared to Jupiter. Here's our sun, 109 times bigger than the Earth, across like this. Suppose we take our sun, which itself is 1.4 million kilometers in diameter, 109 Earths, and we bring it down to make it look like the period at the end of a sentence, 0.5 millimeter in size. Okay? Imagine taking our sun, 109 Earths, and shrinking it down to the size of a period. Where would the nearest star be? The nearest star, this one right here, whose true distance is 4 light years, would be 14 kilometers away. So on a scale where the sun is a period at the end of the sentence, the nearest star is 14 kilometers away, some way down the Bosporus, you could think. Okay? That's the nearest star. And the other stars are much farther away. Here's our Milky Way. You go out to a very dark night sky away from Istanbul, and you look up, and there are just hundreds and thousands of stars. The Milky Way. They are much farther away than the nearest star, which is only 4 light years away. They're much farther away. And we have this view, this streak in the sky, because we live in a galaxy, the Milky Way galaxy, which viewed from the side looks something like this. It's perhaps 100,000 light years across, a few thousand light years thick. And when we, looking from this direction, look through the galaxy, we see lots and lots of stars. So our sun is out here somewhere. And when we look along the plane of the galaxy, we see the Milky Way. And when we look in other directions, we don't see the Milky Way. So that's what you're seeing when you're seeing the Milky Way here. You're looking along the plane of our galaxy. Viewed from above, our galaxy would look something like this. It's called a spiral galaxy. It's got spiral arms like this. Now, this isn't our galaxy, but this is what our galaxy would look like if we could see it from the outside. And it's about 100,000 light years across, and it has several 100 billion stars. So think of this as suns. Several 100 billion suns, all gravitationally bound in our Milky Way galaxy. Let's go back to our analogy where the sun, 1.4 million kilometers across, is brought down to the size of a period, 0.5 millimeter. How big would our Milky Way galaxy be? Well, our Milky Way galaxy is 100,000 light years across, but on this scale, its size would be about 320,000 kilometers. That is nearly as distant as the moon, if you squish our galaxy down. So size scales in the universe are enormous. Our nearest big neighbor is the Andromeda galaxy, 2.5 million light years away. So when you're looking at that galaxy, you're seeing light that originated, that left the galaxy 2.5 million years ago, when early hominids were wandering around on Earth, as I will discuss on Wednesday. When you look farther and farther away in the universe, you see farther and farther back in time. The finite speed of light gives us a movie of the history of the universe. Clusters of galaxies, like this one, can contain thousands of galaxies, and they can be tens or hundreds of millions of light years away. And in this photograph, called the Hubble Ultra Deep Field, taken with the Hubble Space Telescope, we're seeing literally thousands of galaxies. All these little specks here are galaxies like our Milky Way, containing tens or hundreds of billions of stars, up to billions of light years away. Look at this thing. And this is a tiny patch of sky. Imagine a grain of sand held at arm's length. Imagine how small that looks. That's the size of this photograph in the sky, yet it contains thousands of galaxies. Over the whole sky, we estimate that there are 100 billion galaxies like our Milky Way, each with billions of stars. And that's just in the parts of the universe that we can see. We now think the universe extends far beyond those parts that we can see. And everywhere it's filled with galaxies. Now, this discussion may make it seem to you that we are just a speck of dust in the universe, of no cosmic significance. You could become kind of depressed thinking this way. But in fact, we are cosmically special. You're not just special to your family and friends and loved ones. Of course you're very special. Who cares about galaxies billions of light years away? You've got you, yourself, your family, your friends. You're obviously very special. But you're also cosmically very special because you're a member of Homo sapiens. And Homo sapiens have an advanced brain that can strive to understand the universe in which we live. No other animals that we know of can do this. Even the simplest cell is much more complex than any planet or star or galaxy. But humans, this incredible structure of cells, has the capacity to think and ask questions. In a sense, through us, the universe can understand itself. If it were just a bunch of physical, inanimate objects, then, in a sense, the universe wouldn't have a way of knowing itself. Einstein, in fact, said the most incomprehensible thing about the universe is that it's comprehensible. It's comprehensible through us, through our brains, through people being curious and inquisitive about how the universe works. Okay, let me briefly discuss a history of the universe and give you now an idea of time scales. I've given you an idea of distance scales already. The universe is about 14 billion years old. In fact, a recent measurement places it at 13.8 plus or minus 0.04 billion years. We know the age quite well now. And we can tell how old the universe is because the universe is expanding. And 14 billion years ago, the matter out of which all the galaxies consist was essentially squished into a tiny little volume. And it started expanding 14 billion years ago. Our Milky Way galaxy is about 13 billion years old. It formed about 1 billion years after the universe formed. And we can tell how old our galaxy is by looking at the oldest stars. Here is a cluster of stars called a globular star cluster. We can tell that this globular star cluster is 13 billion years old. The Earth and the solar system are about 4.5 billion years old, 4.6. And we determine this through radioactive dating of meteorites, rocks that come in and occasionally land on Earth. These are rocks that are left over from the formation of the solar system. And through radioactive dating, you can figure out how old they are. 4.5 billion years old, 4.6. And moon rocks are a consistent age, about 4.4, 4.5. Took a little while for the moon to form, and we haven't necessarily found the oldest rocks, but it's consistent. Single-celled life on Earth appears to have arrived 3.5 billion years ago, maybe even 3.8. There's chemical evidence for life on Earth 3.8 billion years ago, but fossil evidence 3.5. There are these things called stromatolites, layers of bacteria. Here are some ones that are living now in Australia. Here are some fossilized ones. These are the oldest known fossils. But our early atmosphere did not have oxygen. Oxygen was built up through photosynthesis. Photosynthesis of cyanobacteria. Okay, they produced oxygen. And by about 1.5 billion years ago, the atmosphere was a few percent oxygen. Now our atmosphere is about 20% oxygen. The Earth was born with essentially no oxygen. The Cambrian explosion, 540 million years ago, was a huge development of life on Earth. All kinds of complex, hard-bodied animals formed 540 million years ago. Prior to that, mostly there was single-celled life, or in some cases multicellular life, but only with a very soft body. No hard-bodied animals. Whereas 540 million years ago, there was a tremendous growth in the diversity and complexity of life on Earth. We see fossils of these little creatures called trilobites, for example. 65 million years ago, the dinosaurs became extinct, along with 2/3 of all other living species, in a giant catastrophe known as the Cretaceous Tertiary Extinction. We think it occurred because an asteroid or a comet crashed into the Earth. It could happen again. Astronomers are now looking for asteroids and comets that might crash into the Earth. By the way, there's a fantastic comet coming at the end of this year and the beginning of next year. Watch for it. It'll be perhaps the comet of the century, or at least certainly one of the best ones in a few decades. It's not going to hit the Earth, but we need to watch out for those that might and deflect them before they hit. Otherwise, we might go the way of the dinosaurs. How do we know that all this happened? We see a giant concentration of fossils of many, many species 65 million years ago. Here I'm challenging a Tyrannosaurus rex at a museum in Mongolia. Progressing forward in the history of the world, early hominids formed about 4 or 5 million years ago. We can see that from fossils. Here is the fossil record of Lucy, one of the oldest hominids known, 3.2 million years ago. And we haven't necessarily found the oldest one, so we think hominids formed maybe 4 or 5 million years ago. They evolved, eventually forming Homo sapiens about 200,000 years ago. Maybe 250,000, we're not sure. Okay, and again, we can tell from the fossil record. Now, let me give you another scale model, as I did for distances in the universe. Suppose we take the age of the universe, 14 billion years, and we scale it down, we squish it down to 1 day, which is 86,400 seconds. Imagine 14 billion years crunched down to 1 day. Then Homo sapiens appeared 1 second ago in this cosmic day. We are a very recent addition to the universe. And a human lifespan of 100 years is 0.0006 seconds. 0.6 of a thousandth of a second. That's your life. Make the best of it. Okay? That's your life on the cosmic day. All right? Well, how did we and everything else get here? Let's start from the beginning. The expanding universe. Edwin Hubble in the 1920s studied galaxies like this one. And he passed their light through a prism, producing a rainbow, a spectrum. We can measure the brightness of the light at different colors or wavelengths and learn interesting things about the objects we are studying. For example, the chemical composition of stars can be determined from these dark absorption lines. This one is due to hydrogen. Here is neutral sodium. This is singly ionized calcium. A trained spectroscopist recognizes these fingerprints. Okay? So spectra are very important. But Hubble could tell that the spectra are shifted toward longer, redder wavelengths, the redshift. And nearby galaxies okay, whose distances he determined, seem to be moving away from us relatively slowly. The redshifts are small. And by the way, the redshift can be thought of in terms of a motion away from you. You've heard sirens moving away from you. The pitch sounds low. That's because while the siren is moving away from you, the distance between consecutive wave crests increases. That makes the wavelength longer, the pitch lower. If the siren is coming toward you, the waves are compressed. It sounds high-pitched, a blue shift. So it goes like that if it passes you, the Doppler shift. Well, light does the same sort of thing. And nearby galaxies had a small Doppler shift. More distant galaxies have a bigger redshift, okay? So it looks like all the galaxies are moving away from ours, but the more distant ones are moving away faster than the nearby ones. It turns out that the correct interpretation of this is that the universe itself is expanding. It's not that the galaxies are moving through some pre-existing space. Rather, we now think that we know that space itself is expanding. And light that is emitted by a galaxy at a particular wavelength gets stretched with the expansion of the universe. Now, you are not expanding because you're tightly bound together by electromagnetic forces. And the Earth is not expanding because it's held together by gravity. And our galaxy is not expanding because it's held together by gravity also. But things that aren't held together, space itself expands, and light expands with it. And you can see blue light turning progressively into redder light, longer wavelength light. And that is the origin of what's called the cosmological redshift. So, from our perspective, we see all these other galaxies moving away from us because they're redshifted. And the more distant ones are moving away faster than the nearby ones. It looks like we are the center of the universe. Here's the Milky Way galaxy. All these other ones seem to be going away from us. Are we really at the center? Do all these other galaxies not like us? Is it something we said, or do we smell? Are all these other galaxies lactose intolerant? Get it? Milky Way galaxy, lactose intolerant galaxies. Or when I talk about the expanding universe to my class at Berkeley, I say, what is it? Are we from Stanford or something? Big academic rivals, okay? But anyway, I like to say it. Stanford is an outstanding university, just not quite as outstanding as Berkeley, okay? Anyway, we don't think we're in the center. If we live in a uniformly expanding universe, then no matter which galaxy we're in, we would appear to be in the center. Let me show you an example of a one-dimensional expanding universe. I have these ping pong balls. Those are the galaxies. And the rubber tube is the space between them. The rubber tube stretches. From the perspective of the orange one here, look at that. You can see my universe just went through a big bang. Yeah, so, see, this is why I never point them toward my eyes, Anyway, I have to replace this rubber. Okay. From the perspective of this one here, the others are moving away. But the same can be said from the perspective of any of them. And in fact, for your notes, for your class notes, I have a picture of this, okay? So they're all moving away from each other. And imagine that the rubber band is either infinite or it wraps around itself like this. There's no unique center. There's no edge. They all think they're at the center. And by the way, the more distant the ping pong ball, the faster it moves away from a given ping pong ball, because every bit of space expands, so the more space there was to begin with, the greater will be the total amount of expansion. So the more distant ping pong ball from a given ball moves away faster than the nearby ones, okay? A three-dimensional example is an expanding loaf of raisin dough. The raisins are like galaxies. They're not expanding. The dough is uniformly filled with yeast. It is expanding. Again, imagine either an infinite bread loaf or one that wraps around. So there's no edges. There's no edge off of which we can fall. Anyway, from the perspective of this raisin, all the others are moving away. But the same can be said from the perspective of any other raisin. All the others move away. And this one started out 5 centimeters from that one. After an hour, it's 10. So it expanded 10 minus 5, 5 centimeters per hour. This one started out at 10, ends up at 20. It expanded at 20 minus 10, or 10 centimeters per hour. The more distant raisins move away faster than the nearby ones because every bit of space expands. Okay, so the more space there is, the more rapid is the expansion. Okay, well, if you extrapolate the expansion back in time, you come to a time known as the Big Bang, when everything was all together. And the Big Bang theory is the theory of the expanding universe. So let me discuss that. How many of you are familiar with this show, The Big Bang Theory? It's a great show. I keep hoping they'll ask me to make a little appearance on it. But anyway, the Big Bang Theory is the following idea. The universe started out in a hot, dense, compressed state a finite amount of time ago. Not an infinite amount of time ago. The universe is not infinitely old. In fact, the age is 13.8, roughly 14 billion years. It has been expanding and cooling ever since that time, ever since that moment of creation, the Big Bang. In the first few minutes after the Big Bang, the universe created the very lightest elements and their different forms, different isotopes. They have different numbers of neutrons. You had protons, hydrogen, deuterons, a heavy form of hydrogen, tritons, light form of helium, normal form of helium, and a little bit of lithium was produced as well. No heavier elements, because the density and the temperature of the universe were not the right values to produce heavier elements. You didn't have the right temperatures and pressures for a sufficiently long time to produce the heavier elements. So only hydrogen and helium, and a tiny, tiny amount of lithium. Okay? All right. That's what was formed during the Big Bang. As the universe expanded, the light within it, the radiation, expanded with it and cooled. That means the universe should still be filled with light from the Big Bang, the afterglow of the Big Bang. This is known as the cosmic microwave background radiation. The typical wavelengths now are centimeters, okay, or millimeters. They're microwaves. And they indicate that the temperature now is only 3 degrees above absolute zero. This radiation was discovered by Arno Penzias and Robert Wilson, by accident actually. Now, our temperature here is not 3 degrees above absolute zero, but that's because we live close to a star. We're in a special place in the universe. The typical place in the universe is very, very cold. This afterglow of the Big Bang has such long wavelengths now because the universe has stretched for 13.8 billion years, stretching the light with it. You can think of this light coming from a very great distance, 13.8 billion light years away, and being incredibly redshifted by the time it reaches us. Another way to think of it is that this radiation reflects the current temperature of the universe. We're like in an oven, but it's a very cold oven, 3 degrees above absolute zero. Okay? Let's make a map of the temperature of the universe, which ends up corresponding with density, different regions having a different mass per unit volume, a different density correspond to different temperatures. And let's map the universe throughout the sky, the temperature. So when you take a sphere, there are many ways you can make a map out of it. One such map looks like this. You've probably seen these pictures like in United Nations and other places. So here's a map of the Earth's surface, all right? Turkey is right there, okay? Here, for example, is a plot of the average temperature in June of 1992 over the Earth's surface. You can see it's pretty warm where you are right here. It's cold in the Arctic regions. Very warm here near the equator, okay? All right. In a similar way, we can make a map of the temperature of space. Here it is, 2.7255 degrees above absolute zero everywhere. In other words, no matter where you look in the sky away from stars, this is the temperature that you see. And this also indicates that the young universe was very smooth, No big variations in density, in mass per unit volume, because variations in density correspond to variations in temperature because of the properties of gases. So the early universe was very smooth. But if it had been perfectly smooth to begin with, we wouldn't be here. It had to have some little tiny lumps, some little tiny variations. And if you subtract this constant 2.7255 degrees and look very carefully at what's left over, you do see little variations, warm spots and cold spots. These correspond to tiny variations in the density of the universe when it was very, very young. This is a baby photograph of the universe. It was about 380,000 years old when light that makes this photograph left the matter from which it came. These little variations are tiny. 1/1000th to 1/100th of a percent variations. The early universe was smoother than a baby's bottom. Okay? This radiation was studied and the lumps were seen by colleagues of mine, John Mather, who received his PhD at Berkeley, and George Smoot, who was a professor of physics in Berkeley. They won the 2006 Nobel Prize in Physics for detecting and studying these tiny little variations. And you might think, these tiny variations are so small, who cares about them? They're not important, are they? Oh, but they're very important. Because from these tiny variations, stars and galaxies and clusters of galaxies formed over time as a result of gravity acting upon them. The dense regions became denser by gravitationally contracting and stealing material from the less dense regions. So a dense region here might steal material from other things, from other less dense regions. If we do a computer simulation, starting with the map of the microwave background, and let gravity take its course over 14 billion years, you see structures becoming denser and denser at the expense of less dense structures. So we're moving forward in time over 14 billion years, and you can see galaxies and clusters of galaxies and superclusters of galaxies forming with giant voids in between them. The growth of structure in the universe over 14 billion years occurred precisely because the universe was not perfectly smooth to begin with. The universe has evolved with time as a result of gravity, that great sculptor of the universe, starting from those tiny little variations. And when we compare the computer simulation with observations, we see a great similarity. Here's a simulation of us flying through the universe faster than the speed of light, I might say. This is a simulation, but based on real data. You can see galaxies and clusters of galaxies and giant groups, filaments, superclusters of galaxies separated by voids. This is exactly the kind of structure that's predicted by the simulations. So it's fantastic that we can now explain the current observed structure of the universe as having been produced by the very slow but steady growth from tiny variations in density that our universe was born with 14 billion years ago. Smoother than a baby's bottom, but had it been perfectly smooth, we wouldn't be here discussing it. We are the outcome of this set of gravitationally contracting dense regions. Now let's observe the evolution of galaxies as individuals. We can do that by looking at progressively greater distances. By looking to progressively greater distances, as I said before, we see farther and farther back in time. So you can think of telescopes as being time machines. By looking at nearby objects and farther away objects and even farther away objects, we're seeing the universe as it was a short time ago, a greater amount of time ago, even longer ago. The finite, that is non-infinite speed of light, gives us a movie of the history of the universe. If the speed of light were infinite, we would see the whole universe as it is right now. But because the speed of light is finite, we can look back in time. So, of course, probably the most famous telescope of the past 20 years has been the Hubble Space Telescope. 2.5 meters in diameter, up in space, where it gets a very clear view of the sky. It's been a magnificent device. I've conducted many studies with the Hubble. The other great telescopes, there are many, of course, but the ones which I use most frequently are the twin Keck 10-meter telescopes on the island of Hawaii in the middle of the Pacific Ocean. These are gigantic things, 10 meters across. By using telescopes like the Hubble and the Kecks and looking 8 to 10 billion years back into the past, that is, 8 to 10 billion light years away, we see that galaxies looked very different. There were a bunch of small, irregular little bits and pieces of galaxies, so to speak. And we can tell by looking at them at different distances and thus different times in the past that they came together and little galaxies grew into bigger galaxies. So here are galaxy building blocks, and here are some 3 to 6 billion light years away, so 3 to 6 billion years ago, where you can see that little ones have been colliding with each other and gradually growing bigger with time. And nearby, present-day galaxies are these giant, mature, spiral galaxies like our own. This looks a lot like our own galaxy would look like if we could see it from the outside, we think. Okay? Now we can see this process of the coalescence of galaxies. We can see them merging with time. Nearby, even, sometimes galaxies get close enough together to merge. Here are two gravitationally bound galaxies that are coming together and slowly becoming one. So they used to be two separate spiral galaxies, and now they're coming together to form one galaxy. They will form what's called an elliptical galaxy, one that does not have spiral arms. We can tell this from the computer simulations. Indeed, our nearest neighbor, the Andromeda Galaxy, is heading our way. It's gravitationally bound to us. It is not expanding away from us like the rest of the universe. It's coming toward us. And in about 4 billion years, I'm sorry, this is a typo. I will fix it in your notes. That should say B. 4,000 million years, 4 billion years. It will start merging with our galaxy. Okay? And the two will form, we think, an elliptical galaxy. Here again is a numerical simulation with modern computers. I mean, computers, almost as much as telescopes, have advanced the study of astrophysics because we can simulate what happens when millions or billions of particles come together, interacting through gravity, merging together. By the way, stars rarely collide when galaxies merge together because stars are so small and the distances between them are so big. 14 kilometers on a scale where a star is like the period at the end of a sentence, okay? So stars almost never collide. But through gravity, they interact, and some stars escape like this. Others become more tightly bound. The thing looks a bit like a train wreck for a while, but gradually it looks more and more like an elliptical galaxy. Groups of galaxies also come together, and again, it takes a few billion years. Here I did not have a typo. Galaxies, in a sense, can be thought of as cannibalizing each other. They eat each other. Here's a computer simulation of galaxies in a group, like the one whose photograph I showed you. And gradually through time, they are coming together, forming a single giant galaxy. So they sort of merge one by one. And you can see this one looks like it's going away, going farther away, but it's still gravitationally bound, so it's now going to turn around and come back. And here are galaxies that pass through each other, but they get slowed down and gradually merge. You can see this one now coming back. There were 4 or 5 to begin with, now there's only 3. Soon there will only be two. Look at this one, passing through, ka-clam! And a lot of stars get sprayed out. Some stars get lost in the process, producing intergalactic stars in space. Others bind together, forming an ever bigger galaxy. So look at that. We started out with 4 or 5. Now there's basically 1. So this is what happens as the universe evolves. Galaxies come together like this. Well, let me end with something that isn't visible at all. Dark matter and dark energy. The things I've been talking about so far are the visible matter in the universe. But it turns out the visible matter is a minor fraction of all that there is. And I will talk about this tomorrow at 4 p.m. in the Rectorate Conference Hall in my university lecture. Let me give you a preview. When we look at our Milky Way galaxy, we can see that it's spinning, it's rotating. And it turns out that it's spinning too fast. The stars would all fly away from each other at that rate of spin unless there were extra gravity holding them together. In a sense, the gravity must be there. It's what's causing the spin, it turns out. To see as much spin as we do, there has to be more matter there, more gravity than that which is associated with the visible stars and gas. Vera Rubin in the 1970s measured this to be the case in most, if not all, nearby spiral galaxies. They are spinning, they are rotating faster than would be expected based on the gravitational pull of the stars that we can see. If you add up all the mass from the stars that we can see and ask yourself, how rapidly should the galaxy be spinning? It shouldn't be spinning as rapidly as it is. Another way of saying that, as I said, is given the rate of spin, unless there's more mass, galaxies should go flying apart. And yet, they are gravitationally bound objects. They are not flying apart. Okay? So, we conclude that there must be a whole bunch of invisible matter called dark matter holding galaxies together, keeping them gravitationally bound. And in fact, that dark matter cannot simply be dead stars that are not emitting much light, or cold clouds of gas that don't emit much light. Some of the dark matter might be that, but only a small fraction. Most of the dark matter, we think, is strange little subatomic particles left over from the Big Bang, and physicists are now trying to find direct evidence for that dark matter. Fritz Zwicky suggested this back in the 1970s. He found that the orbital speeds of galaxies in clusters of galaxies are also too big to be explained by the amount of mass that appears to be associated with the light that we see. In other words, if the speeds are real, then clusters of galaxies should fly apart unless there's extra matter holding them together, dark matter. So dark matter is in clusters of galaxies as well. Okay, and there's other evidence for dark matter, which I won't go into right now. An even bigger surprise came in 1998 and has been verified in the 14 years since that time. The universe is expanding. That's been known for the better part of a century. But it's expanding faster and faster with time. This is not what you expect. When you throw a ball or a roll of tape up, the gravity of the Earth slows it down in its upward journey. Eventually it stops and comes back. So if anything, we expect the universe to be slowing down in its expansion. Instead, it appears to be speeding up. And I was part of 2 teams that made this discovery in 1998. And it's been confirmed since then by other observational techniques. And we attribute this accelerating expansion, almost like an anti-gravity, to a new mysterious substance which we call dark energy. Both dark matter and dark energy are dark. They're invisible. We don't know what they are. So we call them dark. They're mysterious. They're dark in that sense too. But they have very different effects. Dark matter binds galaxies and clusters of galaxies. Dark energy causes the space between clusters of galaxies to expand faster and faster with time. A discovery that has revolutionized physics. And the leaders of the two teams that made the discovery were honored with the 2011 Nobel Prize in Physics, as was my postdoctoral scholar, Adam Rees, at the time that we did the work in the mid to late 1990s. He was working with me. We were analyzing the data, and he was the primary person involved in analyzing the data. But he was my postdoctoral scholar at the time. And it was wonderful to go with these gentlemen to the Nobel ceremony in December of 2011 in Stockholm. The rules are that the Nobel Prize cannot be given to more than 3 people, except the Peace Prize, which can be given to organizations. But in the sciences, they can only be given to 3 individuals. That's unfortunate, because there were 51 people associated with this discovery. Nevertheless, it was fantastic to be part of the discovery. So here is our modern view of the contents of the universe. Dark energy, 70% of all the stuff in a sufficiently big volume is this weird dark energy. 25% is dark matter. Only 5% of the universe consists of the stuff that was the main subject of today's lecture. The matter that we can see, the stuff made out of atoms and molecules. That's a minor constituent of the universe. But an important one, because it's the stuff of which we are made, it's the stuff of which stars are made, and it's the stuff which allows us to trace the evolution of matter in the universe. But I'll talk more about the acceleration tomorrow. Let me summarize then the main points, and you will have all these notes. The universe is enormous compared to us. We are like a speck of dust. But we are very complex, and we can understand the universe, and this makes us cosmically special, as well as, of course, special to your own family and friends. Time scales in the universe are very long, very, very long, 14 billion years. The universe is expanding. The space between clusters of galaxies is stretching. The universe began in a hot, compressed Big Bang about 14 billion years ago. The Big Bang produced only the lightest elements, 75% by mass hydrogen, 25% helium, a tiny, tiny bit of lithium. The cosmic microwave background radiation is the afterglow of the hot Big Bang. It's the best single piece of evidence that the universe used to be hot and dense. Initially, the universe was very smooth, but not perfectly smooth. That's good for us, because galaxies, clusters of galaxies, and superclusters of galaxies grew from those little density variations and became separated by gigantic voids. Galaxies evolved by colliding and merging through time. And finally, ordinary matter is only 5% of what there is, a relatively recent discovery. Dark matter, 25%, and dark energy are mysterious components, but dominant components of the universe. And much of physics and astrophysics right now is being dedicated to trying to figure out what these things are. Thank you very much for your attention. And we have maybe 1 minute for questions, and I'll stick around for a little while if you have questions but don't have another class to which to go.
30 seconds for thank you.
Okay.
I think you can see why Professor Flippenko was elected 9 times Best Professor of the Year in a row in Berkeley, which is a record break. The national professor of all the U.S.
Thank you. Thank you very much. A pleasure to be here. We'll have fun in your other classes, and if you wish, you can come up and ask me some questions based on my material or anything else that you want to ask me.
Thank you very much. I enjoyed it very much, and I learned a lot.
Glad you did. I'm so honored that you, as president, as rector, came.
Come on Wednesday, maybe, yeah? Okay, or Tuesday. Yes, very good, thank you.